All right. So I can double check, make sure that it is recording now. The audio is good. And so I posted two announcements. I just want to kind of briefly go over the announcements just so that you guys know what each one is. The first one is a event planned by both Uber and Mesa, which is downstairs. But anyone can attend this one. Okay, so this one is not limited to only members of Mesa. So anyone can attend this one. Um, so from the description, okay, right here, launching a career can be challenging when it comes to becoming an engineer. Preparing early and creating a plan can ensure a successful future. Join us to learn more about how to visualize and execute your goal of becoming an engineer. So it's not even specific to Uber. So for those of you who want to become a software engineer or a computer engineer, or anything within the STEM field, I think this may be beneficial. So that's one. And then the second one is hosted by one of our psychology professors. So she planned this one at about this time of the year because this is right about the time when people get stressed out. And I'm one of the reasons why people are getting stressed out by this time of the year because of all the midterms, exams, and stuff like that. So if you are thinking that you want to learn more about stress management, this is a what we call a college hour event. So you can attend this one. Unfortunately, the two events overlap. So you can probably only go to one or the other because one starts at noon, the other one starts at 12:15 on the same day. The only way you can go to both is to go to this one. This one is in person, and then you go to the other one by Zoom, and you just put one headphone on, so you can listen to both at the same time. I'm not sure whether that's going to work or not. For sure, it's not going to work with me, but for some people, they might be able to get it to work. So there you go. Okay, just resources, events that you might be interested in. So with that all said, we are now going back to the floating point number discussion. And we already talked about the conversion from last time. I went through the entire process to give you the binary bit pattern to represent a specific value. I think it was, okay, this is just from my own memory, I think it was 216.625. Does that sound familiar to you? Okay. So, so we went through that process. If you had a chance, okay, after Monday to kind of go through the lecture again, and this time to take notes and also to repeat, some of the processes, repeat some of the steps, that will help sink in. Okay, you might want to start with a different value. Okay, so instead of 216 and 625, you want to kind of choose a slightly different number, but it will help you kind of consolidate all the concepts that you have learned in class if you kind of went through your own process to replicate all the steps. So what we'll do today is we're going to focus on base 10 to base 2 conversion. In other words, if the focus of this class is really just to look at, how do we represent a value, we are done with that part already. Okay, there's not much else to do, for that part. So what we are doing now is to look at the conversion process between base 10 scientific notation and base 2 scientific notation. That's going to be our focus at this point. So the first part, what I'm presenting here is the description of the syntax of a base 10 scientific notation. We talked about this on Monday already, so I'm not going to spend much time today to kind of repeat that particular discussion. Partially because I'm not going to test you. Okay, none of your exam will talk about regular expression, so it is not part of the scope of this class. I'm only giving you this exposure because I think it is going to be useful in your future as a software engineer or as a developer. So I just kind of wanted to introduce the concept, but there's really no way I can test whether you understand these concepts or not in this class. Okay, but it doesn't mean it is not of value. Okay, so if you have time, you want to investigate further, you can go back to this section here. What we'll be doing instead is to go focus on section 5 because the code corresponding to the regular expression is already done. Okay, I have already written that code for one of your projects or two of your projects next week. So next week we'll be actually doing some programming. So if you are kind of a little green on pointers and structures and stuff like that, this would be a good time to kind of review those concepts, pointers and structures. Okay, make sure that you remember what those things are and how to use those as pointers and structure in terms of C++ syntax. All right. So the first thing is um, a particular value, like 216.625, can be expressed using this portion here. So I'll explain what this portion is. At the beginning, we are going to start with the sign is the same. Okay, so if you look at how I use the sign, if the sign is a 1, then the ternary expression returns a -1. If the sign bit is a 0, we return a 1 for the entire expression. So the sign bit is really just saying, okay, is the entire value positive or negative? That's all it's trying to specify. A sign bit of 1 means the value itself is negative, and a sign bit of 0 means the entire thing is negative. Okay, if it's a 1, the whole thing is negative. If it's a 0, the whole thing is non-negative. So it really has nothing to do with base conversion. That's just the sign by itself. So initially, we are going to be given with a coefficient that is specified in base 10, followed by a exponent of 10 as well. So this really is the value that we want to represent. It's only this part here. And then we want to convert everything so that we end up with a coefficient that is in base 2. And the coefficient is not really the important part. The important part is we only want to specify the rest of the value using a power of 2. The power of 10 should be completely gone. Is that okay? So the exercise that we went through the other day actually completed this entire process. So what I'll do is I am going to go back to the example from last week so that I can kind of talk about this a little bit. So give me a little bit of time here so I can start up the tablet mirror and move it into some place that you can see. There we go. Okay. So last week, or not last week, on Monday, we talked about 200. Oops, I was using the wrong tool. Okay, here we go. All right, so we started off with 216.625, and in base 10 scientific notation, it is 2.16625 times 10 to the power of 2. Are we doing okay so far with this one? Okay, so this is the C++ notation when you want to express a float or a double. Okay, now one thing that is really important, because I observed that yesterday with the Tuesday, Thursday lab, is on your calculator, this E over here may not be a single lowercase e on your calculator. It depends on the brand of your calculator. In the case of a Casio calculator, this lowercase e is usually the key itself is labeled exp for exponent. If you have a TI, it would be the key that has the uppercase EE in it. Okay, so most of you have TI calculators, so you have to find the key where combined with one of the function keys will give you the uppercase E followed by an uppercase E, because the lowercase e is referring to the natural log exponent of the natural log constant. So it's not going to do what you think it's going to do. Syntactically, it will look right, and it won't even complain about it, but you won't get the result that you need. Okay, so just a little bit of warning. Okay, so we talked about how this base 10 scientific notation eventually boils down to a binary representation, and I have the binary representation worked out from Monday, but since I don't have it with me right now and I don't want to kind of go back to the other pages, I will just go ahead and work it out again. So this time, I'll just kind of work it out really fast. So we have 128 plus 64 plus, do we have a 32 after that? 192. So we don't have a 32. And then we have a 16. And let's see, do we have an 8? Okay, well, okay, I'm going to do the actual math here. So there's an 8. This is a 8 over here. 64. We have a 4. We have a 2. Then we move on to 16. So we have an 8. Okay. So that's the entire part for the uh, non-fractional part. And then the fractional part is a 0.5 because 0.625 has 1.5 in it. And then the leftover is 0.125, and that covers the entire value. So when I convert this, it becomes, okay, since this one has dots, it really helps. So I can have a 1 followed by 128 is 2 to the power of 7. So I have 7 zeros after the 1. So we have 1, 2, 3, 4, 5, 6, 7. The 64 is just one place. I have to move the one with one place. And then the 16 is 1 followed by 4 zeros because 16 is 2 to the power of 4. And then we have the 8, which is 1 followed by 3 zeros. And then we have the 0.5, which is just 0.1 over here. And then we have the we have the 8th, which is a 0.001 over here. So after you add up everything, then we have, oops, that one's supposed to be a 1. Okay, and then we have 0, 0, 1, 1, 0, and then 1, 1 over here in base 2. And now we have to convert it into a base 2 scientific notation so that we have our mantissa and also the exponent in base 2. So this becomes 1.1100101 in base 2 times 2 to the power of, I believe, 7, because we have to move the point exactly 7 places. 1, 2, 3, 4, 5, 6. Oh, okay. Okay.
Missing 1 0.
I think I'm missing a 0. You're correct. So that means we have to insert a 0 here. Now it's right. Okay, but we completed the whole process. So we know how to do this by hand. The question is, can we do this, in an automatic way? Okay, not so much automatic, but programmatic. Okay, because you still have to write the program. So why do we want to convert from base 2 scientific notation, which is basically what the double is, into from base 10 scientific notation, or what would be the reason why we need to do that? Okay, I will give you I'll give you an idea. Okay, next page. So when you write a C program, you can have a double, x, so x is a double, and then you say C in greater than x. And so, when you run this program or this fragment of code, um, unless you have redirection and some of the other things, the computer is going to stop on the command line and you type in a number, and that number will be stored into X. Okay, I hope you learned at least that much from your CISP 360, right? Okay, so the question is, how does X get its value? Because when you type in the number, it is in base 10. So how does it end up with a actual double precision floating point number, which is essentially a base 2 scientific notation when it is stored in X? That is the reason why we are going through this discussion, okay? Because we want to understand how this is done. By understanding the process of how this is done, it will reinforce your understanding of scientific notation. It will reinforce your concept about the double precision floating point number format, and it will also reinforce a lot of the other math concepts, as we'll see later. Are we still doing okay so far with this discussion? Okay, all right. So, but given this is the context, so now we're going to move on and talk about the two cases. So there are two specific cases that we need to talk about. It is outlined in section 5. So when you look at section 5, particularly section 5.2, it is broken up into two subsections. we have section 5.2.1 where the exponent of 10 was initially less than 0, so you have something e minus something. And there's another case when the exponent of 10 was originally more than 1, so you have e45 or something like that. So we'll deal with this one first. 5.2.1 is the case that we have to deal with first. So I'm going to slide back to this entire discussion here. So the idea is, how do we get rid of the exponent of 10? Okay, because when you get rid of the exponent of 10 by adjusting the mantissa or the coefficient and also the power of 2, by the time you have a 0 for the exponent of 10, you would have everything else figured out already. Okay, so that's why we are focusing on this little equation here. At any time of the conversion process, the value that we want to represent minus not considering the sign itself, because the sign is a simple thing. We don't want to even bother to talk about the sign. So the value itself is expressed by some kind of a coefficient. Okay, so this coefficient is not a mantissa. Okay, it is just a coefficient, but it's not the coefficient of base 2 or the coefficient of base 10. It's kind of like a mix of the two. Okay, so look at this coefficient just as a particular integer, okay, or natural number because it's non-negative, times some power of 2 times some power of 10. So when we're in the process of converting, then you end up with E2 being non-zero and E10 being non-zero at the same time. The idea is we want to bump E10, okay, from a negative value all the way up to 0. But in the process of doing that, we are going to have to change the coefficient and also the power of 2 or E2. So when you're done with the entire process, when E10 eventually becomes 0 because you keep incrementing it, then we end up with the representation that we want, or very, very close to what we need. So we're doing okay so far with that concept, that this is the intermediate representation of V. All we are trying to do is to start with E10 being some negative value, E2 being 0, that's our starting point, and we want to reverse that so that E2 ends up with something that is most likely non-zero, and then E10 becomes 0. So that's the whole process. Are we doing okay so far? Okay. So what I'll do next is to show you mathematically what we are talking about here. So let me switch back to the tablet and we'll just write this out. Okay, V, the value that we want to preserve as much as possible. Okay, it's not entirely possible to preserve the entire thing, but we want to do this as much as possible. It is some kind of coefficient times 2 to the power of the exponent of 2 times 10 to the power of some exponent of 10. Okay, so this is just a replication of what I showed earlier in the module. So now the math part is to basically say, how do we do this? So assuming the E10 is negative to begin with, let's say negative 45, okay? So we'll plug in actual values, okay, to basically say, how do we do this, okay? So I'm going to use a particular number, say 1.23 times 10 to the power of negative 45. Okay, so this is a non-negative value, but it is very close to 0, okay, because it is times 10 to the power of negative 45. So one thing about this entire conversion process is I don't want to use anything that depends on floating point numbers. Okay? In other words, I don't want to use log. I don't want to use power. I don't want to use sine, cosine, or the floor function, or the round function, or anything like that, because all of those rely on the floating point representation. I want to only rely on integer operations. Okay, so I'm going to emphasize that also here. We only want to rely on integer operations. So, okay, why is that the case? Why do I put this limitation to the entire process? Okay, so can anyone kind of guess why I want to impose a limitation of, oh, we cannot use log, which is actually quite handy in situations like this. So why do you think I want to avoid the use of log to the power of all those other functions that rely on double or float representation? It has to do with hardware, okay? And this class really is about hardware as well, okay? All right, so since there are no answers, I'm going to kind of dive into that a little bit, okay? So there's something called an FPU inside every single processor core, and it is not one of these. It's called floating point unit. There we go. All right, so the floating point unit is a component on most modern processor cores. So when you buy a new computer, like that has a i3, i5, i7, i9, processor, or anything from AMD of equivalent processing power, they all have at least a few, not just one, a few floating point units, FPUs on each core. So if you have a four-core processor, you end up with four times that amount. Okay, so which is cool, right? But when you look at the actual processor on a Fitbit, it most likely does not have an FPU. The processor on a cell phone, maybe. Okay, I'm not really sure. So for anything that requires low power, they don't have an FPU. Can anyone imagine why that is the case? Okay, so all you have to do is to analyze the statement itself. The question answers itself. Okay, why do you think that anything that requires low power does not have an FPU? So if you analyze the question itself, okay, what are the key elements? Yes.
Because it has low power, it's not going to need to require the floating point unit.
Not so much that it does not require, but you're onto something. You're picking out the key components of the question that will eventually answer the question. Yes, go ahead.
Are FPUs really power intensive?
Yes. So FPUs are power intensive. They require extra silicon on the die, and even though you can power down, the die, that portion of the a die is basically the physical thing, the silicon that is inside the processor. So the FPU is actually a significant portion of a processor core. So if you have the FPU and you use it, that basically uses up, energy, and so your battery life is going to go down. A lot of things that we think, okay, from the perspective of convenience, require floating point unit calculation can be converted to something that does not require floating point calculation, which then reduces the power consumption of the device, which then increases the battery life, which then improves the marketability of the product. I mean, who wants to wear a Fitbit thing that needs to be recharged every 2 hours? I certainly would not want to have a device like that. Mine, it needs to be recharged every 5 days or so, which is already much better than many of the other wearable devices. I think Apple Watches need to be recharged what, daily? I mean, you guys, some of you have Apple Watches. Is that daily? Yeah.
Mine's old. The battery's also down.
Well, the new ones, with more processing power, they always find a way to use that processing power and still needs to be recharged on a daily basis because they just find, oh, we can now do all of these other things that use up the power, the energy as well. So that is the reason why I don't want to rely on floating point calculations. Now, you can perform floating point calculations without a hardware FPU. That used to be done on every single PC. Okay, back in the days of the 386 processor, the FPU was an extra chip that you have to purchase, which is really quite expensive, that you plug onto the motherboard. Then you have the FPU to perform floating point unit calculations faster. But unless you pay for that, okay, you'll be using the regular CPU, which cannot do floating point unit calculations by itself. It's all basically software code doing it. So you can either trade energy, okay, with the code complexity, which boils down to energy as well, okay. So I don't want to deal with either one, okay. I want to be able to do it fast and not to use a lot of energy. So that is why we have this restriction. Okay, that's why we have this restriction of only using integer operations. Is that okay? Does everybody understand the rationale behind why I want this restriction? Okay. All right. So the next thing now is we have an immediate problem because if you look at C, the coefficient, and you look at what is legitimate as the coefficient, it can be 1.23, and 1.23 is not is a floating point number. So that means I have to store the whole thing as a floating point number. Yes.
Are you recording?
That's a very good question, and let me double check. Yes, so the audio is good, and it says stop recording, which means it is recording because the button says if you click me again, I'm gonna stop recording. So thank you for checking, because I know how I missed that on Monday. Yep.
And the V equation, what is that?
Say the one more time.
Oh,
sorry.
the V equation, what does that?
Oh, V is the value. V is the value being represented. Okay. All right. All right, so the first question is, what about the 1.23? That's an easy one to handle, because I can now say, let's use 123 as our coefficient. It does not qualify as a mantissa anymore, because a mantissa has to be
Greater than 1, but less than the base, right?
greater than or equal to 1, but very good, okay? Really close. So we have 123 times 10 to the power of what? If I want to preserve the value being represented, what should be the new exponent? Go ahead.
43.
Negative 43. Okay, negative 43. But yes, it is negative 43. Okay, cool. So now the coefficient is a unsigned integer. The exponent is a signed integer. This one has to be signed. But nonetheless, I don't have floating point numbers anymore because I just got rid of the 1.23. It is now 123. Are we doing okay so far with this? All right. So now we have this thing, okay, we have 1.2 v, this particular v is 1.23 times 10 to the power of negative 43, and I'll just kind of tag on a times 2 to the power of 0. Well, I can always tag on times 2 to the power of 0, because 2 to the power of 0 is 1, so it doesn't really change the rest of the product. So now I have everything in the format that I need. The C, the coefficient, is 123. Sorry about that. I forgot about the point. The point should go away. Oh, maybe that's not a point, right? Did I have a point earlier? I did?
I think so.
Okay, so that should not be a point because we converted that to an integer already. So it's 123 times 10 to the power of negative 43 times 2 to the power of 0. Okay? So we'll think about just one thing first, okay? How do I change the power of 10 from negative 43 and bump it up to negative 42?
Make C 1,230.
Okay, when you bump up the power of 10, you are increasing the value by tenfold. Not increasing, but you're multiplying the value by tenfold. So that means there has to be a division with the coefficient. Okay, let me write it out. Okay, so because we want to preserve the value, so we want 123. Now I intentionally put 123 up there, okay, for a reason. Okay, so this part is identical, but then I say, is that okay? We have multiplication by basically a 1, because 10 divided by 10 is a 1. The question is, how do we express that 10 divided by 10? Okay? So what we'll do is I changed my mind, I'm going to rewrite this in a slightly different way. So I am going to use color coding in this case, and we'll use the magenta color to basically say, the multiplication by 10 is going to grouped with this part here, okay? And then the division by 10 is going to be done by this part. So what I end up with in this case is 123 divided by 10 times 10 to the power of negative 42 times 2 to the power of 0. So let's just pause here and make sure that you are okay with the algebra involved in this calculation. Yep.
Is it supposed to be negative 43 or negative 47?
Sorry?
It's supposed to be negative 43 or negative 47.
It's negative 43 It is negative 43.
But if you move it to the,
Okay, let me double check the math, okay? Because I am negative 47. You are correct. I'm moving in the wrong direction. Okay, so let me go back and change that because I made a mistake. This part here should be a 47. Okay, well, let me just change that. Okay, go back to the pen tool. Because when I increase, when the mantissa is 100 times what it used to be, then the exponent of 10 has to be decreased by 2, not increased by 2. You are correct about that. So go back here and change that. This one is a little bit strange. So we'll do that. And then we also have to change the last one here. And that should be now 46. Very good. Excellent. Somebody is paying attention. All right. But the key point here is how we divide the 10 divided by 10, how we chop it up and put the multiplication by 10 and associate it with 10 to the power of negative 47 so that we end up with 10 to the power of negative 46. And the division by 10, the denominator is now associated with the um, coefficient. Are we doing okay so far with this? But thank you for the math correction. So is that part okay? Are we okay with the algebra of the whole thing? Yep.
Doesn't that just make it a floating point number again?
No, because we can use integer division. So, but the problem with integer division is it's no longer exactly the same because now we are looking at, oh, that's just 12. Because when you perform integer division, 123 divided by 10 is really just 12, which means now we have a problem because we have an error. Is that okay so far? That we end up with an error. What is the error here? Let's take a look at the error. The error is the 0.3 divided by what the answer is supposed to be, which is 12.3. Okay, this is the error rate. Is that okay? Because the recorded answer is 0.3 short of what it really should be. So the error rate is 0.3, which is the actual delta between what it's supposed to be, divided by what it should be. So that's the error rate. Are we doing okay so far with this discussion? Everything from the algebra perspective of how this turns into this. And then now that we are looking at the fraction as an integer division, we end up with an error because it is supposed to be 12.3, but the integer division will only end up with a 12. So we end up with an error rate of 0.3 divided by 12.3, which is about, well, I'm going to guess it's about 2.5%-ish, okay? You can do the calculation and find out exactly what it is. So now the next question is, I don't like errors. Okay, so how do we fix this? How do we minimize the error? Well, we can do something like this. Okay, so we are I'm going to skip over to here and say, maybe I can do something like this. So I'm going to pick a power of 2 that is not too extreme so that we can at least look at the quantity. Okay, times 10 to the power of negative 46 times 2 to the power of 0. Okay? Would anyone object to the introduction of 64 divided by 64? It shouldn't matter, right? 64 divided by 64 is just 1. And if you introduce another times 1 in the product, it's not going to change anything. Are we good so far? Okay? But the question is, how do we associate the 64 as the numerator and the 64 as the denominator? Okay, which one goes where? So now the question is answered by, I'm going to use color coding again, and this time I'm going to pick neon yellow. Okay, there we go. So I am going to associate this 64 with the power of 2 over here, and I take it back. Sorry, my bad. My bad. Okay, so this 64 is associated with 123, and then this 64 here is associated with the power of 2. Okay. So what is the end result? Okay, so let's take a look at the end result here. So the end result is we end up with, I need to do the actual calculation so that we actually have a number to talk about. So let me go to my calculator. 123 times 64 is 7872. So we have 7872, the whole thing divided by 10, times 10 to the power of negative 46, times 2 to the power of negative 6. Okay, I think that is correct. Yep, it is. Okay, so let's pause here again, okay? Are we okay with this algebra? All I did was to say, oh, okay, this is 64 divided by 64, but because the whole thing, this 64 divided by 64 is in a product, so I can use the commutative law and basically say, oh, the 64 can be moved somewhere, and I'm just going to associate it with the 123. So 123 times 64 becomes 7,872. Those are all base 10 numbers. What about the division by 64? Well, the division by 64, I'll re-express it as 2 to the power of negative 6 and associate it with 2 to the power of 0. So when you have 2 to the power of 0 times 2 to the power of 2 to the power of negative 6, you end up with 2 to the power of negative 6. Is that okay so far? So I really should not have changed the value being represented, and hence the equal sign. It goes all the way back to b itself. Except now that when I do a division, this division here is integral. Okay, it's an integer division. So I end up with something that is also less than perfect, but we'll check out the error rate this time. So this becomes 787 times 10 to the power of negative 46 times 2 to the power of negative 6, and I still have an error rate. The error rate in this case is 0.2 divided by 787.2. That is my new error rate. Can you compare between these two error rates? Which one is higher? The top or the bottom? The top one has a much higher error rate because it's in the region of about 2.5%. The bottom one has a much lower percent error. Does that make sense? Okay, so the only thing that caused the error rate to go down is because we have 64 divided by 64. Does that make sense? Does it make sense that if I change this 64 to a much higher power of 2, then we would reduce the error even further? Yes? Okay? So what we'll do is we're going to say, we're going to maximize that power of 2 so that the result of 123 and the power of 2 would just barely fit in a 64-bit number. Okay? So some of the questions in today's lab has to do with that. Okay? How do we find the largest power of 2 to multiply to a certain number so that the product will still just barely fit in 64 bits? Okay, so that's going to be one of the questions in today's lab. Are we still doing okay so far? Okay, so that solves one problem. What this is doing, it solves the problem of precision. Okay, we can try to maintain as much precision as possible by maximizing this power of 2. Is that okay? Conceptually speaking, are we okay with what we are doing and why we are doing it? We good? Okay. All right. So I'm gonna write. Where's my stylus? Okay. I was just using it and now I cannot find it. um, oh, right here. This is called the I'm an unintentional magician. Magician can make things disappear intentionally by creating optical illusions and whatnot. I can do that without intention, which is a special talent. Okay, so what we want to do, okay, so I want to copy and paste some portion of this. Let me select which portion. Okay, that works. So we do a copy, new page, paste, and then move it to about here. Okay. Switch back to my pen tool. Okay, so now we can continue the discussion. So one of the things that we have to do is to basically say, we have this, we want to find some power of 2, like p, to multiply the whole thing, so that we end up with 123 times 2 to the power of p before we divide the whole thing by 10, times 10 to the power of negative 46 times 2 to the power of 0 times 2 to the power of negative p. And so the algebra should still work, okay, right? And the idea is to find out what that p is supposed to be so that I can maximize the accuracy. Is that okay? So I'm generalizing the whole thing and saying, okay, we just have to find out how much we have to multiply to 123 so that we can preserve the value as much as we can. And then when we do the division, we're not going to lose a lot. Okay, we're going to lose a tiny little bit. Because as a 64-bit number, okay, this portion is supposed to be a 64-bit number. So how many decimal digits do you think a 64-bit number that's kind of maxed out is going to take up in decimal digits? Okay, remember that trick that we talked about earlier? How 1024, which is 2 to the power of 10, is about 1,000, right? Okay, let me write it out. So 1024 is uh, is 2 to the power of 10, which is about 3. Okay, I cannot get the orders right. 10 to the power of 3, which is 1,000. Okay, so we use this as an approximation. So that means 2 to the power of 64 can be seen as 2 to the power of 10 to the power of 6, then the whole thing times 2 to the power of 4, which is approximately 10 to the power of 3, that whole thing to the power of 6 times 16. So this does equal to 16 times 10 to the power of 18. Are we okay with this estimate? So what is it telling you about the number of base 10 digits when we have a number that barely fits within 64 bits? How many digits are we talking about? Okay, well, if you look at this number, 16 times 10 to the power of 18, how many decimal digits is it going to take? That should be a question that you can answer. Yep. 18 zeros plus the extra,
So 19.
yeah, 19 digits. Yep. So when you divide a 19 base 10 digit by 10 and you lose, just one of those digits, the fractional part of the loss in terms of accuracy is pretty small. Does that make sense? That's a fire drill signal. All right. Well, since it's a fire drill, so we are going to.
It's not a fire drill. It's the like FEMA
Oh,
thing.
okay.
It's a national thing.
Oh, so it's not the actual thing.
It's just all of our phones.
Well, it's buzzing my ear because my Bluetooth is connected.
Wireless emergency alert system.
Is there an actual emergency? That's the question.
For testing.
They announced that there
It's
was
just
gonna
a
be-
test.
Okay.
Yes.
They said there was gonna be a test today, but that wasn't happening.
I'm not going to share with you my devious plan if I were a terrorist. I will not say anything because I think if I did say that, the Homeland Security people will come here and take me away. So I will not say a single thing. But a thought just occurred to me. It's like, oh, if I were a terrorist, this is like a golden opportunity. That's all I'm going to say. Nothing else. Okay. It's scary that I can even think of that, but anyhow. Okay, so yes, so this is the best way to minimize the error. But we have a problem with this approach too, because every time we have an error, what is the direction of the error? Let me rephrase that. Is the actual result smaller or higher, or bigger, larger than what it is supposed to be? So we are looking at a general problem like this. Okay, we have some kind of number. We'll call that C. We divide it by 10. Okay, but this is an integer division. Okay, it's an integer division. So the question is, how do I compare this versus this? So the other way to look at the integer division is you perform the division normally, but then you take the floor function of that. C is non-negative. So the question is, what operator should go here? Is it less than or greater than? Or well, less than or greater than? Less than or equal to or greater than or equal to? That should be the proper question. C is non-negative.
Wouldn't it be greater than or equal to?
That is correct. Okay, so this question mark is always going to be greater than or equal to, which means we now have a new problem. Okay, so even though the error is small each time you perform that division by 10, the integer division by 10, but every single time you perform that division, the error is only going in one direction. So in computer science term, we have a biased error. The bias is always in one direction, which means if you do these things enough steps, you end up with a significant bias because every single time you have an error, it always errs on one side. So that means if you perform these operations multiple times, then the error will all add up and you end up with a value that is quite far away from where it should be. Is that making any sense? Okay, and that's not a good thing. Okay, this is not a good thing. So that means we need to perform rounding instead of just taking the floor of something. So the question is, okay, that doesn't seem hard because all you have to do is now to say we'll just take a rounded result of that division and we have done. We'll be fine here. There are two problems with this. In order for round to work, you have to give it a floating point number. Remember how we are not supposed to be using floating point calculation? So that's the first problem. The second problem is C divided by 10 is an integer division, which means you don't have a floating point number to begin with anyway. So this method is not going to work. So what we'll do instead is we'll analyze what rounding really is doing and then see if we can convert that to just using integer operations. Yes?
Can you use mod?
You can use mod. Mod is a pretty expensive operation, so you can use mod to inform you whether to bump it up by 1 or not. Okay, so that's one way to do it. But the easier way to do it is like this. So let me introduce the method, and then you guys can look at this and say, does that make sense? So I'm claiming that this is really just that. These two are identical. Okay, so we'll take a look at this. And in this context, the division is not an integer division. In this context, the division is actual division. So we'll go through a few examples just to see whether it works or not. So we'll start with some concrete values like 123. C is 123. And we say, what is this? This is the round of 12.3, which is 12. But what is 123 plus 5 divided by 10, and then take the floor of that? You have 128 divided by 10, and then take the floor, which is also just 12.8. You take the floor of that, which is also 12. Huh. Seems to work.
No.
What?
12.8 has to be like rounded to 13.
Nope. Nope. This is taking the floor. This is just taking the floor, which is the largest integer that is less than or equal to 12.8.
Oh.
That's the floor. Yep. So floor is the same thing as a truncation. You basically just get rid of the fractional part, at least for non-negative values. All right. So that seems to work. Let's try something else. Okay. So on the next page, we'll try something a little bit different. So we'll try 77. Okay. So we look at the round of 77 divided by 10, and that would be the round of 7.7, which is an 8. Okay. We try the other method. We look at 77, we add 5 to it, divided by 10, and that becomes what? 82 divided by 10, which then becomes the round of 8.2, which is 8. That works too. So this method is kind of cool because it's replacing the round operation. You're getting the rounded division, but only using a single addition and a single division using integer operations. So in the realm of modern processor cores, this is a really inexpensive operation. It doesn't consume a lot of power. It gets the job done, and it's pretty easy to understand. Are we doing okay so far with all this math stuff? Okay. So we got Go ahead.
So you're basically adding 0.5 to the.
Yeah.
Okay.
Yep. But 0.5 itself is a floating point number. I cannot do that when I restrict myself to only integer operations. But you are correct. The plus 5 then divided by 10 is essentially adding 0.5 to the original result of the division. But I express it in a way to only utilize integer division. Is that okay? All right. Okay, so this is great because now we have two techniques, okay? One technique is about precision, okay? So if I were to go back to the slide here, this technique here preserves precision, okay? Great. And then the other approach, which is, let me go back here. This approach here is going to, it will remove the bias of the error, okay? Removes bias in the error. It is okay to have error, just not biased, okay? Because if the error is not biased, then sometimes it will lean one way, other times it will lean the other way, and in time, they usually kind of just cancel out. So now we have both of those problems solved, which means if we are to rewrite, oh, okay, that's it. Yeah, okay. So if we are to rewrite, this thing here, this portion here, let me go ahead and drag it around and rewrite that. So use the lasso tool, and we copy that, and then we move it to the last page, paste over here. So there's only one thing we have to modify to basically say, this is the whole thing, okay? Yeah, we can now perform that one step, okay? With the only thing we have to do is to say, before we divide it by 10, add 5 to it. That's the one thing, okay? Because adding the 5 before the division by 10 is doing the rounding. Maximizing p, which is the power of 2, is going to maximize accuracy or precision. So now we can do both. They go like, okay, so what was the whole, why are we doing this again? So that we can change the power of 10 by 1. So the power of 10 was originally 10 to the power of negative 47. It is now 10 to the power of negative 46. We bump it up by 1. Yay! They go like, and then what do we do? Well, we do the same thing again. Okay, we look at whatever quotient is left. Okay, so we take this number here and we say, okay, this is another coefficient, we call it C1. So now the value is now approximated by C1 times 10 to the power of negative 46 times 2 to the power of negative p, whatever p turns out to be. So what do we do now? Well, since we still have a power of 10 that is not 0, what do you think we're going to do? Exactly. Okay. So in my mind, I have Pinky and the brain, having that conversation where Pinky will ask the brains, so brain, what are we gonna do tonight? And the brain is gonna say the same thing we do every night: try to take over the world. Okay. You guys are way too young to know what is Pinky and the brain.
Yeah, I know.
It's classic. I really like Pinky and the Brain. So anyway, we do it again. Okay, we basically look at C1 and then we ask, okay, go find me a P so that I can multiply C1 by 2 to the power of P to max out, to use all 64 bits. And then we add 5 to it, divided by 10. Then we can bump the power of 10 up by 1 again. It becomes negative 45, and then we just keep doing the same thing until the negative 40 something becomes 0. Eventually, it will get to 0. So are we doing okay so far with this entire discussion? Okay, all right. So I'm gonna take roll right now. So we'll have a little bit of time for you to kind of let this stuff sink in before we continue with more stuff. All right, so the road taking activity is not, you cannot see it yet. So let me go there, unhide it first. Okay, so here we go. You should be able to see the road taking activity, which is 2023 1004. And the access code is regex, REGEX, which is the abbreviation of regular expression. Regex. Yep.
Did you unlock it?
I did, but the time I forgot that I set the time to 11:30, so I have to change that. Sorry about that. When my watch buzzed, I was still in the middle of a discussion, so I didn't take roll at the time. So we'll change it to 11:50. That should be sufficient time. Like so. Save. There we go. So go ahead and refresh it. It should let you in this time. But the access code is regex, REGEX. All right. Okay. So I'll let you guys complete the roll taking activity first, and then I'm gonna move back to here to talk about the other direction. What if you're given an exponent of 10 that is greater than 0 to begin with? What do we do in that case? All right, so I'm just checking. Most people seem to be done. We have a few people who are still looking at the screen somewhere. Okay, so now the question is, so this is basically section 5.2.1, except I just use a more or less numerical example to illustrate it. So now we move on to section 5.2.2, which is basically saying, what if you're given an exponent of 10 that is greater than 0? So we'll go ahead and look at 1.23 times 10 to the power of 45. Okay, this is the original number. So the first thing we do is, okay, let's turn the 1.23 to 123. Now this time I have to decrease the power of 10 by 2, so it becomes 43. So this time it is 43. The other time it was 47 because I moved in the wrong direction. Okay, so now what do we do? Well, the first thing we do, same thing that we did before. is to introduce the power of 2 as 0, because we can always introduce that without changing the value of the product. Okay. Then you look at this and go like, okay, so this time we want to decrease the power of 10 until we get to 0, right? But we can play with C, we can play with, which is the 123, and the power of 2, so that we can make all of those adjustments. The question is, how do you do that? So what do you think? How do we decrease the power of 10? So I'm going to work on this really step by step. So I'm going to say 123. We use the same trick here. We multiply by 10 divided by 10. The only question is, which 10 goes where? Okay, that's the question. So we look at this and go like, well, since we are supposed to decrease the power of 10 by 1, so that means the grouping is going to look like this. I am going to divide the 10 to the power of 43 by 10. Therefore, the new power of 10, or the new exponent of 10, is going to be 42. So that means the 10 multiplication by 10 is going to be associated with 123. Okay, so let's see what happens this time. We have 1,230 times 10 to the power of 42 times 2 to the power of 0. That works out, not a problem. It looks like all that division stuff, the rounding stuff, didn't need to happen at all this time. You'll be correct, okay? Not yet. Because at some point, it's going to have to happen. Why do you think I said, yeah, at some point it's going to happen? Because we have 10 to the power of 42 here. So can someone tell me again, with a 64-bit number, not even a 52, with a 64-bit number, how many base 10 digits do we have? 19 digits, okay? Between 18 and 19, kind of depending on the most significant digit. So we'll just say between 18 to 19 digits. So that means, using this approach, I can decrement the power of 10 from 43 up to 19 times. Then we are running out of space in terms of the coefficient. The coefficient will no longer fit in a 64-bit number. Okay, then what do we do? So I'm just going to say, at some point, the coefficient is becoming C or C0, okay? And it is times, let's see here, so 1,230 is using 4 digits already. So we have 15 digits left, okay? So I'm just going to guess, okay? 42 minus 15 is 27, I think. Okay. Okay, we'll just theoretically say that, okay? The actual detail, needs to be kind of worked out, but I'm suspecting I can get it to this form where C0 is using all 64 bits of a 64-bit unsigned number. So let me qualify that. So C0 barely fits in 64 bits. Okay, so that's a qualifier, because if I multiply C0 by 10 again, it's going to blow up. It's going to go like, oh, okay, I cannot store that product anymore. Is that okay? Does everybody understand what I mean by barely fitting in 64 bits? It means if I multiply one more time by 10, it's going to blow up. Okay? So now what do? We are running out of space. Okay? Well, this time I'm going to work with something like this. So I'm going to go like, what if I were to do this? Okay, go like, oh, so that's kind of a trick that we did before, but we have never seen 2 divided by 2. We have only seen 10 divided by 10. Well, but 2 divided by 2 is still 1, so I can still kind of use this approach. So now the question again is, where do we multiply by 2 and where do we divide by 2? That becomes the question. I cannot multiply C0 by 2 anymore, because C0 barely fits in 64 bits, which means not only the next multiplication by 10 is going to blow up, the next multiplication by 2 is also going to blow it up. Okay, so we cannot do that. So that means the only way to associate these calculations is to associate the division by 2 with C0, and then associate the multiplication by 2 to the exponent, the 2 to the power of 0, which is a power of 2 already in existence. Is that okay? All right. So I'm going to rewrite this whole thing. Okay, so we'll go like, okay, so we end up with C0 times 2, oh, not times 2, divided by 2. And I intentionally leave some space here. The whole thing times 10 to the power 27, which was kept from before. And then the power of 2 becomes 2 to the power of 1, because we are multiplying 2 to the 2. We are multiplying 2 to 2 to the power of 0, and therefore we end up with 2 to the power of 1. Is that okay? Now, at this point, I'm not really sure whether C0 divided by 2 has enough room for another multiplication by 10. I don't know yet, okay? But there's one problem here. We have a division by 2, and it's an integer division, which means we have to round it. And this time, how do we round it? Just based on, even without understanding the math at all, okay? Based on how we did the rounding when we had to divide by 10, what do you think I should do this time to round it? Add 1, exactly, half of the denominator. Okay, so this time we just say, this will do the rounding. Okay, so then we look at this thing here. We look at this number. We'll call this C1. And then we have to ask the question, do we have enough room for another multiplication by 10? In other words, we have to ask, if I multiply C1 by 10, is that going to be greater than or equal to the largest number, the maximum number, if I want to use 64-bit unsigned as a representation? If it is still larger than, then I have to do it again. Okay, I have to basically divide C1 by 2 again, and then bump up the power of 2 by 1 again. So I have to keep doing that until I have room for another multiplication by 10. Okay, so I'm going to pause and see whether that is okay with you guys. Does that make sense? Because one division by 2 is not going to clear enough space for another multiplication by 10, for sure. Because 10 is between which two powers of 2? 3 and 4. Okay, so that means at the minimum, I need to do this 3 times. But even 3 times may not work, because there are occasions where you need 4 times. Okay, so instead of predetermine whether it's 3 times or 4 times, I'll just keep doing this until there's enough room, until this condition becomes false, until C1 or whatever the coefficient is times 10 is less than the maximum value that I can store in 64 bits. Then I can stop the division by 2. Then I can go back and do the multiplication by 10 again, and therefore decrementing the power of 2, decrementing the power of 10, so we are one step closer to where we need. Okay, so I'm gonna finish this whole thing. So we're gonna say by the time we get to C3, okay, so I'm just assuming that we only need to do this 3 times. So by the time we did get to C3 times 10 is less than this number here, the maximum 64-bit unsigned integer value. Then we can actually carry out the whole thing. So now we end up with then we can multiply the coefficient by 10 again. So now we have C3 times 10 becoming C4, the new coefficient, and then the power of 10 becomes 10 to the power of 26, and then the power of 2 is going to be 3, because we said that we have to do it 3 times. Is that okay so far? So after all of these steps, what have we accomplished? So if I were to highlight it, we went from here, where we have a coefficient that barely fits within 64 bits. The power of 10 was 27, the power of 2 was 0. Now we end up with a new coefficient that also barely fits in 64 bits. the power of 10 is now 26, and then the power of 2 is now 3. Woohoo! We are one step closer because we just changed the power of 10 from 27 to 26. But now that we know how to do this, it's just a matter of, oh, okay, keep doing this again and again until we get to 10 to the power of 0, and we're all done. Are we doing okay so far with the mechanism of these kind of conversion? Okay. Um, is anyone starting to appreciate all the algebra stuff that you learned in your math classes? I mean, this is really just algebra stuff, okay? This has no trig in it. There's no calculus whatsoever in it. In fact, for most developers, the chances of you encountering calculus again is actually kind of slim, okay? But your calculus classes help train your reasoning, the way you process, the math problems and so on. They're all going to be helpful when you become a developer or a software engineer. So all of that is useful. Okay, it's just that it may not be immediately useful, for whatever you want to do as a career. All right, so that pretty much concludes, the whole conversion thing. It doesn't go all the way to a floating point representation. So let's kind of check out what we need to do when we end up with, c times 2 to the power of p as v, because that's eventually what we want to become, because the power of 10 eventually becomes 0, so that just goes away, becomes a 0. And in this case, c is going to be just barely less than 2 to the power of 64, and it's going to be greater than or equal to 2 to the power of 63. Yeah, so this is the constraint for the coefficient when everything is done, okay? Because we want to maximize our accuracy, and c, the coefficient, is what is controlling the accuracy, okay? So if this is what we end up with, we want to kind of convert this into the floating point number representation. What do we need to do? Well, the first thing is c is not a mantissa, okay? Because it's a huge number. In base 10, it's going to have between 18 to 19 digits, right? So what do we do? So this c is basically a gigantic base 2 number where there are 64 bits, and the binary point is all the way here. And we need to move that binary point. We need to move this binary point all the way over here. So the question is, how many times do we have to move it?
Sorry, if the max number of digits you have is 19, you have to move it around 18.
No, 64. There are 64 bits because we are looking at the base 2 representation.
So around 63.
63 is correct, okay? So this means, we have to move the binary point 63 times to the left. What is that going to do to this power of p here? So the new exponent of 2 becomes p, and we have to do something with 63. So the question is, are we adding 63 or are we subtracting 63? We're adding, because every time we move the binary point to the left, we are making the coefficient half of what it used to be. So to make up for halving the coefficient, we have to multiply somewhere by 2, and that's done by increasing the power of 2. So this is a plus, okay? So the next question is, okay, that answers one of the questions. Now this is the non-biased exponent, so that means the biased exponent, okay, if I look at the biased exponent, that's just going to be p plus 63 plus 1023, because 1023 is the biased amount, okay? That was on Monday's lecture, why we have a 1023 here. So biased exponent, which is the bit pattern that goes into bit 52 to 62, this is how we compute it. Yep.
I thought it was minus 1023.
Well, the conversion from non-biased to biased is to add 1023, and then the conversion from biased back to non-biased is a subtraction of 1023. Yep. So this basically becomes bit 52 to 62, or the binary representation of that expression becomes bit 52 to 62. Bit 63 is easy because that's just sign bit. We don't need to have to talk about it much. So now the question is, what about bit 0 to bit 51? That's the remaining portion of the number. What are those things? It's the fractional part of the mantissa after we move the point, right? So basically, we go from here. This is bit 62 of C, okay? And then we just go like, take a bunch of these things, go all the way down to, let's see, we need 52 bits for that. So that means we have to go down to bit, I cannot do arithmetics. I think it's 11. So from bit 62 down to bit 11 of the coefficient C, all the way up here, okay? These will basically become bit 0 to bit 52, a bit 0 to 51. So that means, oh, okay, so that's an easy way to do this. All we have to do is to make sure bit 63 become a 0, and then we perform a right shift operation. How many times? 11 times. Then we end up with the fractional part of the mantissa. So that's why I said when we get to this part here, the rest is pretty easy because it doesn't matter whether the original power of 10 is a positive or negative value. We just have to blindly do all this stuff here. Okay, the bias exponent is whatever this p is, which is reflected up there, plus 63 plus 1023. Get the binary representation of that, and put those into bit 52 to bit 62. And then bit 0 to bit 51 is basically just recycling bit 11 to bit 62 and shift everything 11 times to the right hand side. And then we're basically done. All right. So are there any questions about this last part of how we go from this part here all the way down to the actual double precision floating point number? In your lab next week, you don't have to do that. Okay, all we need is to get to this point here, and I consider it done. Yes.
So then, do you just lose the precision of those last 10 bits or so, or 11 bits?
11 bits. Yep. Mm-hmm. So basically, what we do, okay, so in terms of the math, what we do is we take C, which is the same as this one here, it's a 64-bit unsigned integer. It takes up all 64 bits, right? So the first thing we need to do is to get rid of the most significant bit. And to get rid of the most significant bit, you do a bitwise AND with the bitwise NOT of 1 left shifted 63 times. Okay, so that will basically clear bit 63 itself. Then what you do is you right shift this whole thing 11 times, okay? And then you take this entire thing, you do a bitwise OR with the exponent, okay, with this expression. But that expression also needs to be shifted 52 times before you do the bitwise OR. So this whole thing here will finish the whole thing up and give you a 64-bit pattern, not counting the sign. The sign is easy. So not counting the sign, this will give you the 64-bit representation of a double precision floating point number representing the same V that we have been talking about. Now, I have tried this algorithm myself and compared that to the internal conversion subroutine in C and C++. And then, as it turns out, this way of doing it is actually very slightly more accurate compared to the C library, the way the C library does it. So, it's definitely not wrong. And you can even anticipate how much time it takes because you already know that we only the power of 10 is limited. Okay, so if you look at the range of what a double can represent, okay, so let me go back to the slide here because I want to point out what about the time complexity. So if you look up here in the double precision floating point number and look at the maximum value, okay, so I'm just going to search for max here. There we go. All right, so the worst we can do is to repeat the loop 308 times, which is not really that much. I mean, if you're dealing with a positive exponent, the negative exponent is about the same. It's just 308 versus 324. Um, but it gives you a estimate of how much time it takes in the worst case to use this particular approach to convert from a base 10 representation to a base 2 representation.
So it's just a linear time complexity?
Hmm?
Just a linear time complexity?
Well, okay, so when you talk about linear complexity, you have to mention linear to what, right? So it is not exactly linear to the width of the uh, floating point number. So it is more or less, well, let me think. It has to do with mostly has to do with the exponent. So depending the exponent determines, or I should say, the exponent or the number of bits to specify the exponent is going to be linearly correlated with the length of time.
Okay.
Yep. All right. So next week we're going to work on actual algorithm that you're going to have to turn in as a C program to get this done. Today's lab, I'm transitioning to today's lab now, is all about math. And I'll give you some starting points, because I think, there will be a few questions. So instead of answering the questions individually, let me first, make it available so that you guys can get in, publish, there we go. All right. So once you get in, you will see 4 different types of questions. They just repeat. So question 1 and question 5 are the same type. Question 2 and 6 are the same type, and so on. So I'll address each one individually. Question number 1. Yes?
What's the access code?
Oh, right. I forgot to mention that. Let me go back to the previous page and see that. It is EXP for exponent. All right. So let me go to the preview. All right. So question number 1 and question 5 are the same kind. And what it's asking is x is a value that is given to you. And I want you to figure out what is p as a natural number. In other words, x times 2 to the power of p plus 5 has to be less than or equal to 2 to the power of 64 minus 1. How do you solve for that p? Sorry?
We're trying to find the maximum value?
Yes. So we're trying to find the largest natural number p so that it meets this requirement. Yep. All right. So how do we solve this one? Since it's a mathematical problem, it is not surprising the answer is mathematical, right? Okay. So the one thing I want to kind of remind you, this is also from Monday's lecture, is if, okay, I shouldn't say if and only if, n is x to the power of y, then the log of x of n equals to y. Yeah, I think that's right. Okay. All right. So given this is the case, okay, and your calculators, oh, okay, maybe I can use the tablet so everybody can see it. Give me a second. All right. So if n equals to x to the power of y, if and only if the log of base x of n equals to y. Okay, so that's one piece you need, because once you can solve for y, once you can move everything to one side, then it's just a matter of taking the log. Okay. Okay. Let me go back to the question so that you guys can correlate what I say here with what the question is asking. The question is giving you a inequality. So for the most part, you can solve it like an equality, except when you solve for p, take the floor of whatever the solution is, then you have the answer. So the question is, can you move everything to one side except for 2 to the power of p? In other words, 2 to the power of p is on one side, everything is on the other side. And treat it as an equality so that you can solve for the actual p, and then you take the floor of that p, that becomes your answer. Is that okay? All right. The other way to solve this problem is really just to use a calculator, and you start with p equal to 1. Try it. Does it work? No. Times 2. Does it solve the problem? No. Times 2 again. You only have to do this up to 60 times, okay? Because it's guaranteed to basically solve the problem within 64 times. All right, so are we okay with question 1 and 5? Okay, so question number 2. The recorder is still on, so we are still recording right now. So the second one is actually a lot easier, okay? It's really just literally asking you, if x is, in this case, 18.57, what is the round of 18.57 divided by 10 minus the floor of 18.57 divided by 10? That's literally what it's asking you, okay? So I probably do not need to explain this one any further, okay? And the way we do the rounding is just like what we talked about in class. Add 5 to x first before you divide it by 10, and then take the floor of that. It is the same thing as doing the round in this case. So that would be question number 2 and 6. The next one, question number 3, is deceptively easy. Okay, so the focus is on the second paragraph. You are given a particular value. Express the value of x in units of 2 to the power of p, where p equals to negative 20. So what it's really asking is this. So we have x and 2 to the power of p. Okay, I just need to make sure I get the nomenclature correct. So you have a number line. Right here we have x. And I'm asking you, how many steps do I need to walk to get to x? So you guys will be going like, well, it kind of depends on what is your pace, right? What is the distance between the steps? The distance between the steps, in this case, is 2 to the power of p. That's it. If you want to look at it from a different perspective, because most people, would wake up and try to pay attention when we talk about money. So it's the same thing as asking, if I have to make change for $13.62, okay? But I only have quarters. I don't have $10 bills, $1 bills, or pennies. I only have quarters. The question is, what is the best estimate of $13.62 using only quarters? How do you answer that question? Division, exactly. So you just have to divide it. What is the actual distance divided by the step size? Then you get the number of steps. The only tricky part about this question is it wants the most accurate number of steps, which can be over or under. In other words, you might end up overstepping a little bit, or you might end up understepping a little bit. Whichever one is closer is the answer. The question is asking how many steps, not asking the actual distance to here or here, but it's asking you how many steps do we need to perform. So it's a division problem. Question number 4 is probably the worst of all the questions, but once I explain it, it's probably one of the easier ones. Okay, well, procedurally it is a little bit involved, but in terms of actually doing the math, it's not too bad. So in this case, I have a particular value, which in this case is 8.678 times 10 to the power of 29. Okay, So I give you a particular value. I want to express that value as some kind of x times some power of 2 so that, okay, this is conjunction, so that x is greater than or equal to 2 to the power 52, but it is less than 2 to the power 53. So you have constraints, okay? You have one constraint of what x has to be, and then based on that constraint of x, what x has to be, and also what b has to be, you have to figure out what that p is supposed to be. Once again, p is a natural number. It is going to be greater than or equal to 0, and in this case, definitely less than 53. So how do you solve this problem?
Well, first things first, you have to make sure that the value of x obviously stays between 2 to the power 52 and 2 to the power 53.
Mm-hmm.
So once you understand that, you need to find the closest value that fits the closest number of p that can fit that
Right.
constraint, right?
Right. But the question is, how do you find p? Because x is not given to you. I'm only giving you the constraint of x. I don't even give you what x is supposed to be. So I just know that we have a coefficient, we have a power of 2. And I want the product of those two to give me a specific value with a constraint that x has to be greater than or equal to 2 to the power 52, but it has to be less than 2 to the power 53. Yep.
You could just you could divide b by 2 to the 52. It's
Yep.
for x.
Yep. Mm-hmm. Well, no, you don't solve for x. So the way you do it is you plug in the maximum value of x, which is 2 to the power 53, plug that in as if that is the value of x, solve for p. Okay? Then, depending on how you want to do this, but the more intuitive way is to plug in x as the smallest value that it can possibly be, solve for p again. Those two solutions for p are guaranteed to be just one off from each other, which means there has to be just one single natural number between those two solutions. And that would be your answer. Should I say that again? Yes? Okay. So plug in the smallest value that x can be, which is 2 to the power 52, solve for p. P is going to be an irrational number. Plug in the largest value that x can be, which is 2 to the power 53, solve for p again. That's going to be another irrational number. But there's only one single integer between those two irrational numbers, and that integer is the answer. That would be your solution. Okay? So I'm hoping that in addition to working out the mechanics of how to figure out the answers, you are starting to see how this relates to the lecture material, because this is what we have been looking for. Okay, is how do I multiply that coefficient so that I have no room for any further multiplication, except in class we did not use 2 to the power 52, we used 2 to the power 63 instead. But otherwise, it's the same kind of problem. So the solution would be, the method to get to it would be very similar. All right, so I have just explained the approaches to the 4 different types of questions. They repeat, so that's why you have 8 questions. I'm going to stop the recorder and upload the recording. So hopefully you wrote down enough that you can get at least the first 2 questions started before you have to go back to the recording for the other 2. Any other questions before I stop the actual recording? I'm still recording right now. No questions? All right. So I'm going to stop the recorder, get it uploaded so that